If it's a horizontal line, he's not going anywhere, right? He's just standing there, like, I'm just chilling out. I forgot how to ride the bike. Okay. So, yes or no, I don't know. So, what are you told about the velocity? Is it positive or negative?
Positive.
Now, this is where you look at this in terms of the sequence. You've got a positive velocity. Is the slope of a position time graph gives you the velocity, right? So if he's going 5 meters per second, look at this. If he's going 5 meters per second, every 10 seconds, how far is he going to go? Don't make this difficult. He's going 5 meters per second. Every 10 seconds, how far will he go?
5 times 10 is 50.
50 meters. Nice. Dear Lord, I know it's Friday, but come on, work with me here. So at the end of 10 seconds, where is he at? 300. The other 10 seconds, he's going to be at 350. Another 10 seconds, he's going to be at 400. Okay. So he's going to end up out here 400 meters away from the reference point. Okay? Now, at the end of that time, what's he going to do?
Turn around.
Turn around. So right away, what happens to the slope of the velocity time graph?
Change the sign.
Change the sign, right? Now, how fast is he going to be going on the return trip back to the tree to pick up his Scooby lunch pail?
It's a negative 10 meters.
Negative 10. So every 10 seconds, on the way back, how far is he going to go?
100.
100. So he's going to be out here at 400, right? And then 10 seconds later, he's going to be at 300. Another 10 seconds, he's going to be at
200.
and then 100 and
0.
back to 0. So your graph should look something like this. Okay? When you get done, that's what your position time graph should look like. So realize that starting at 250, he's going away, and he's going to go all the way back to the reference point. Now, keep in mind there's two distinct parts of this trip. When you're talking about displacement, remember it's always final minus initial. So on the way out, he's starting at 250, he's ending at 400. On the return trip, he's starting at 400 and ending up at 0. Okay, and remember it's always final minus initial on how you calculate that displacement. Okay? Does that help clarify? Jones, are we good?
Yes.
Okay. Anything else you want me to go over? Yes, Vonda.
Number 11.
Number 11. Okay. Well, let's talk about 10 and 11 because they're all kind of part and parcel of the same thing. So I'm going to show you some different ways you can work either one of these problems. Okay. Let's actually start with number 10 because math is going to be a little easier. So the speed of sound is about 330 meters per second, roughly. Okay. So here's the deal. Think this through. Speed of sound is 330 meters per second. It sounds simple, but it's amazing how often I see this get screwed up. If the speed of sound is 330 meters per second, every second, how far does this sound wave travel?
330.
330 meters, right? Okay. So in the end of 2 seconds, it would travel 660. 3 seconds is going to be 990. So here's the deal. So here's a lightning strike, okay? And you're standing 1,1609 meters away. And you're standing here, right? And you want to know how long that sound wave is going to take to travel. So right away, since the speed of sound is 330 meters per second, is my time going to be more than 1 second or less than a second? More. Why? Why is it going to be more than 1 second?
1,609 is greater than 330.
Yeah, because if I was 330 meters away, it would take exactly 1 second. So since I'm more than 330 meters away, I know my time has to be more than a second. So if your answer to number 10 is less than a second, you have done something horribly wrong. Okay? Now, let's figure out how you can solve this. I'm going to show you 3 different ways you can think about number 10. I don't care how you do it. I'm going to show you 3 different ways. Okay? And here's the thing. The more different ways that you acquire to solve the problem, the deeper your understanding is going to be of the problem, okay? So try and avoid being like a one-trick pony, okay? Be able to think through problems in a variety of ways. So one option is you go, oh, Mr. Burkamp, I love formulas. I'm happy for you, okay? I'm happy for you. So here's a simple formula. Y'all have had this equation probably since 5th or 6th grade. Distance traveled is equal to velocity times time. That's it. So do you know the distance? Yep, you know the velocity. So what's the thing you don't know? Time. So how are you going to get time by itself? What are you going to do?
Divide by v.
Yeah, so take distance and divide by velocity, and you're going to get time, right? Okay. Now, here's what you all do wrong. I see this more often than anything else. What you do wrong, do not do what I'm about to do. Here's what y'all do wrong. For whatever reason, y'all decide to take velocity and divide it by distance. Okay, that's what you do. No, don't shake it. No, we won't do that, Mr. Burkamp. Whatever. Okay? Now, here's where this is wrong. This is meters per second divided by meters. Well, the meters cancel out, but do you get seconds?
No.
No. What do you get?
The inverse of seconds.
You get 1 over seconds. Okay? 1 over seconds is not seconds. Now, here's what you cannot do. You can't sit there and go, and I've seen kids do this, like they will come over here and write 1 over seconds, like when they're working the problem. They will write this down. But they go, I don't know what to do. And so they'll come over here and they will write the wrong answer, and then they'll just magically write seconds. Okay? People, if your dimensional analysis produces units of 1 over seconds, wishing it away and just writing seconds over here isn't going to fix the problem. Okay? If the units don't work out, the units don't work out. And you writing down an answer from the oracle isn't going to make any difference. It's still wrong. Okay, so that's one way you can work the problem. Another option is you go, Mr. Burkamp, I like geometry. I like shapes. Always been a big fan of shapes. Okay, good. I'm happy for you. So, the other way you can work this is actually on a velocity time graph. Okay? So, here you've got the speed of sound, about 330 meters per second. That's their height, right? That's going to travel for some amount of time, which we don't know. But now, how does the 1,609 meters play into the problem on a velocity time graph? How does this fit with this? It's a velocity time graph.
Area.
Area represents
Displacement.
displacement. So you could sit here and go, oh, the area of this triangle, which you've all known for quite a while, is length times width, right? So the other thing you could sit here and go, oh, this area is 1,609 meters. That equals the length, which I don't know, which is my time, times my height, which is 330 meters per second. Ah, look, you do the same math. You're going to take the area, divided by the dimension of height, there's the time. Okay? That's another option. So if you like geometry, this is one way to view it. Oh, it's a geometry problem. Now, some people like ratios. So the other thing that you can do is look at this and going, okay, I got a velocity of about 330 meters, and I'm going to write this over 1 second. Right? That's what that number means. 330 meters per 1 second. So if you like ratios, you can go, okay, well if I got 330 meters per 1 second, that's going to equal 1,609 meters over X number of seconds. Ah, cool. So 330 over 1 is going to equal 1,609 over X. How are you going to get X by itself? Cross multiply and divide. Guess what? You're going to take 1,609 and divide it by 330 meters per second. It's the exact same math, right? I don't care how you understand it. Just understand it. Okay? So 11's the same thing. Okay? Look on 11. You're given a distance, you're given a velocity, you're solving for time. Okay? That's it. It's the exact same thing. Nothing new under the sun. Okay? And your answer to number 10 should be a really, 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 really good GPA. Really, 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 really good. Okay. And your answer to number 11, not so good. As in, oh, wow, yeah, did you even show up?
You don't need to make fun of my GPA.
Huh?
You don't need to make fun of my GPA here.
I just said, I didn't mention any names that are McGriddle, you know?
If you're feeling so conscious about it, maybe.
I'm not passing judgment. Okay. Anything else you want me to go over? Going once, twice. So stay with the graph to the back. Give that hint in.
This right here. Because technically right here, it's accelerating. Yes.
So Max,
Flip off the camera.
Poke your head in there. They need to know who grape is.
I was giving a thumbs up and I realized.
There's grape, guys. They need to know who grape is.
There's grape.
That's grape.
Yeah.
got a lab.
Hey, we need to rock you music together.
Look at the football. Look at the football players.
Yes, it's in third trade down.
They're twinning.
I can't wait.
It's a football thing to do.
I feel like I'm more fun. I can't wait. You're welcome. I'm so excited.
All right.
What?
So here's the setup. I've got yonder cart. I'm going to give it a push, and what's going to happen is that Nick is going to stop it. Okay? So I'm going to give it a push. Nick's going to stop it. Now, this is also going to be true of the lab. Do not include the push. Okay? The push is not part of the story. So wherever I let go of it, that's the reference point. Okay? The velocity is not going to start at 0. Okay? It's already moving. Okay? Don't include the push. Y'all struggled with that yesterday. Don't include the push. Now, all I want you to do is watch what's, kind of get an idea of what's going to happen, right? But we are going to include Nick stopping it. Okay? So, just observe what happens, right? So, here's the reference point. We're going to define that direction as being positive. Okay? You ready? Just stop it. No, send it back again. That's that. We'll bounce later.
I didn't expect it to bounce off like that.
Okay, you ready?
Yeah, I'm cool.
Oh, here.
There we
Okay,
go. There it is.
All right. Okay? So what would the position time graph and what would the velocity time graph look like? Now, let's start with some general observations. Do you think the cart slowed down a little bit as it went?
No.
It did a little bit.
Just a little.
Okay? Now, it's not like I flipped it over and I had the metal side down. Okay? Because if I do that, let me see. Yeah, if you flip this thing over, it's like, oh, that was fine. Okay? So, right? So, there's a little bit of friction, but not much. Just a little bit. So, here, now, get that back over there. So, here's what we've got. There's a couple of ways that you can look at this. We'll deal with the position time and the velocity time graph later. So, here's the cart. And I gave it some initial velocity, V1. Okay? I don't know what it is. I don't care what it is. Okay? We'll worry about that later. So, as the cart rolls, 3 things can happen to this velocity vector. What's one thing that could happen?
Stay the same.
Decrease.
It could get smaller. It could get
Bigger.
bigger.
It could stay the same.
Or it can stay the same, right? So what do you think's happening as it rolls?
Get smaller.
Just a little bit smaller. Not rapidly, okay? But there's a little bit of slowing, okay? Now, this falls under the category of Jedi Stowful, okay? You stop the force and you watch. I stopped applying a force, and we're going to watch what happens with the cart, okay? Now, Mother Nature is lazy. Mother Nature does not like to change velocity vectors. As soon as you establish a velocity vector, that's what Mother Nature wants to keep, because it costs energy to change velocity vectors. Mother Nature goes, quite frankly, I don't care, okay? So some things, if that velocity vector is changing, that means there has to be a force acting on the system. So, you start here with V1. V2 is going to be a little bit smaller, not noticeably. You know, it isn't like, whoa, we're going to hit it, you know, with a hammer or something, right? But it's going to slow down a little bit. And then you're going to get out here to V3, okay? And then that's even going to be smaller. So whenever you see velocity vectors change, what's happening?
Acceleration.
Acceleration. Now, here's what's important, especially on this lab, and from here on out. You cannot accept the idea that acceleration only means speeding up. If this velocity vector is changing, either in magnitude or direction, that is acceleration. So when I talk about acceleration in this class, you're only talking about a velocity vector that's changing. It might be speeding up, but it might be slowing down. Okay? So you've got to get that into your minds right now. So these velocity vectors are getting smaller. So here's the question. Is it accelerating?
Yes.
Yes. Now, your acceleration vectors, which are also vector quantity, so because it's a vector quantity, it has
Direction.
and
Magnitude.
So, which direction do you think the acceleration vectors are pointing? They're either pointing to the left, in the opposite direction of the velocity vectors, or they're pointing to the right in the same direction as the velocity vectors. Why left? Slowing down. So therefore I have positive velocity and
Acceleration.
therefore I'm going to
Slow down.
Beautiful. Beautiful. Makes an old physics teacher heart proud. Okay, so do you think your acceleration vector is going to be very big?
No.
No. Okay, why?
Because you don't speed that. You don't
Yeah,
slow
I'm
down
not changing rapidly. Okay? So I'm going to have some small negative acceleration vector, some small negative acceleration. Okay, right? Point this way. Now, what happens though when it hits Nick's hand? When Grape stops it, what happens?
quickly. Stops altogether.
What happens to your acceleration? It goes,
Gradually,
Jones, what'd you say?
gradually like declines and stuff.
Yeah, so you're slowing and then all of a sudden, bam,
Like
right?
rapidly, yeah.
So is bam a big acceleration or small acceleration?
Big.
Big. Oh, big acceleration, right? Big, right? So when it hits Grape's hand, these velocity vectors change rapidly, right? And whenever you get a rapid change in your velocity vectors, that requires a big acceleration. Now, if you look at that sign, if you want to have a big acceleration, what else do you have to have?
Big force.
Big force, right? Because you can't create a small acceleration, or excuse me, you can't create a big acceleration with a small force. Dog won't hunt, right? So as your acceleration gets bigger, your force has to get bigger. Now, with all that said, what's the position time graph going to look like?
It's just going to be getting bigger and bigger and then stop at some point and level out. 'Cause
Bigger
if
and
we're-
bigger. So something like that?
Yeah.
Yeah.
Everybody cool with this?
Yeah.
We need to tweak it a little. We need to tweak it just a little bit.
Oh, it's curved down just a little bit.
So here's the question. Should it curve up like this and then level off? Or should it curve up like this and then level off? Vonda, you were the first one to say it should be this first curve up like this. So we'll call this the Vonda curve. Okay? Vonda, why is that your curve?
Because it starts faster and gets slower.
Beautiful. Okay? And if you come in here and you draw your tangent lines, oh, look what happens, right? So you've got your biggest tangent lines here, and then as you go, those lines become more shallow. Now, Grape stops it very quickly. So why does it, what's happening when this thing levels off?
It's not going any further.
Yeah, it's just, it's stopped. It's just staying right there. Okay? Now, what's the velocity time graph going to look like? Here's 0 meters per second.
It's going to start out high.
Yeah, it's high.
It'll start out high, okay?
Start out high,
gonna be-
slowly go down and then immediately stop at some point.
So this line can do one of three things. It can go up, it can go horizontal, it can go down.
Go
It's gonna
down.
go down.
Go down a little.
A little, why?
Well,
It's
because,
not decreasing.
I mean, it's
Yeah,
so, yeah.
look at your acceleration vectors, right? You have small acceleration vectors. So therefore, the slope of my velocity time graph is pretty shallow. But when it hits Grape's hand, because then we have a,
Big move.
which means we have to have a steep line, right? So yeah, we're going to be humming along, and then bam, right? Okay? Bam is indicated by this, right? Bam, boom, okay? Because you get a big change in velocity in a small amount of time. Good with that? Nice. Okay. Now, back over here. Okay, now on this one, it's more complicated now. More complicated. Okay? Okay, so here's what I want you to do. On this one, I'm going to push it. We're not going to include the push. I want you to stop it for just a little bit for dramatic flare, and then I want you to push it back to me.
Okay.
Okay? So I'm going to push it, stop it, send it back.
Okay.
Got it? Okay. Okay. So what would the position time and the velocity time look like? Hunter?
Do we count your stop?
I don't include my stopping it.
Okay.
So it's still moving when it crosses that reference point. We're going to include, we're all about great, but not about me. Okay? So we're worried about great, we want to show that, but not including me.
Okay.
So, what's going to happen?
Go on here.
Well, let's go back to the velocity vectors. Are the velocity, is this still representative of what's happening going in?
Yes.
Yes, right? I've got positive velocities, I've got some negative acceleration. Now, brake's going to stop it, so we're going to get some big acceleration, right? He's going to stop it. We're going to pause for dramatic effect. Now, on the way back, what's going to happen to these velocity vectors after he lets go of them?
It's gonna sort of,
Stop. And then they'll.
Right?
it's gonna
So,
be big and then starts aggressive.
yeah, you're going to have big, right? But after he lets go of it, then they're going to get smaller. So as it's rolling this way, what's the direction of the acceleration vectors? Right. So now I have positive acceleration vectors. So what's creating this acceleration? Something has to be causing this. No. This is after he's let go of it. Or after I've let go of it. What's creating the acceleration? Friction. Now look, if you're going this way, which direction does friction act? Against it. If I'm going this way, friction acts to the right. So where do you think friction acts relative to motion? Opposite direction. Friction is never going to make you speed up. Friction's always going to act in the opposite direction of motion. Okay, which is a cool thing because otherwise when you hit your brakes, you'd go faster. But, oh, I got to slow down. Hit my brakes. Woo! Okay, bad. All right. So, let's go back to this. Here's my position time graph, right? This is when Nick has stopped it. So let's kind of let's just start over from scratch. We bonded. We still have the Vonda curve going in. Okay. We still got the Vonda curve. Now what's going to happen? Level off for the dramatic flare. Then what?
It'll have a sharp.
Tumbling down.
It's gonna,
Tumbling down. Sounds like a nursery rhyme.
It's gonna be like
Humpty
a
Dumpty goes
It's gonna
tumbling
be a
down.
Vonda.
Now, I'm going to give you three curves, what I call the Mick Jagger lip curve. Okay, if you've ever seen Mick Jagger, his lips are huge, and I'm all on Mick Jagger. Okay. No, seriously, his lips are huge. So, you got A, B, and C, right? What?
That's so good.
No, it's true.
Yeah.
His lips have it so many times out there. All right.
I predict Jesus. I predict A.
I didn't realize when you
Oh.
were Mick Jagger and
Why A?
Because you start out with a high velocity, so you're going back quickly, but then you start to slow down as friction acts upon it.
Okay. So what would B indicate? What would the middle of the lips indicate? Is that what happened?
No.
No. C would be kind of cool to watch. What would C indicate?
Positive acceleration.
Yeah, he pushes it, and it starts slow, and then it gets closer to me, and it speeds up. It's be cool.
It's your gravitational attraction.
You're not the first one to tell me that. So anyway.
You just call him fat, man.
All of you have it. Mine's just bigger because I weigh more. Back off, okay?
I don't know.
So roasted.
Yeah. Okay. as my birthday approaches, I think you could make like for physics, it only makes sense for physics teachers. You have like the equation E equals mc squared, energy equals mass times speed of light squared. As you get older, like that changes and your energy decreases because it changes into mass. Whereas if you're young, you have all of this energy and not much mass. But as you get older, like it tips and energy turns into mass.
I've got a lot of that.
Yeah, it's a sad thing. Okay.
Ouch.
That's harsh.
That was.
Okay, so everybody cool with A. Why is A right? Because A is going to indicate what?
Fast.
Starting fast and going slow. Cool with this. What's the velocity time graph going to do?
It's gonna go.
Is this still going to be cool?
Yes.
Then what?
It's gonna.
This is when grape has stopped it.
Okay, it's gonna pause a little horizontal line on 0 for a little bit.
Yeah.
Okay? A little horizontal line action, then what?
It's gonna
Shoot
be
up.
Will it shoot up?
No.
Oh no, shoot
Will it be-
down.
Because
Or will it shoot down?
Change
Oh,
direction.
down.
Oh, it's changing direction.
So it doesn't. Yeah.
Oh,
So
because if you send it up, what would have grape done?
You would have pushed it
Grape
farther.
would have pushed it in the same direction. Should have been cool. Didn't happen. So what's it going to do?
Shoot down.
It's going to shoot down, but then as it rolls, what's it going to do? Go up, stay horizontal, or go down?
Stay horizontal with the tendency to go up a little.
No, it's like
Gonna keep going down.
Well,
This is the point that grape lets go of it. He is no longer pushing it at this point. So it can either do one of three things. It's either going to slope up towards 0, it's going to be a horizontal line, or it's going to slope away from
Slope up
0.
towards 0.
yeah, it's gonna start sloping up towards 0.
Towards 0 or away from 0?
Towards
0. Because what's it doing as it rolls?
slowing down.
So now, if you send it away from 0, what's it doing? Speeding up.
so why doesn't our first line do that on the first part of it? Why doesn't angle it down? If it's slow.
It does angle down.
Oh, does it?
Yeah, that's supposed to be an angle.
Okay.
Yeah, it
Because
does.
I thought that. Okay.
Yeah, it's just not much. But then, bam, right?
Yeah.
Okay.
Why do we
Now,
have,
here's the last thing. What? Do you have a question?
why do we have 2 BAMs?
Because we got a bam when it stops and then a bam when he pushes it. So this is a 2 bam system. Okay?
Got 2
But we have a
bams.
dramatic
Jagged
pause in
bits.
between the bams. So we go bam, pause, bam. Okay? Makes sense. It's a BPB, you know, bam, pause, bam. Okay? Right? Now, but now we're going to eliminate the pause and we're just going to go one big bam. Okay? Whoa. Whoa. Okay, now, here we go, right? So, we got a camera. Big bam, here we go.
I'm not stopping it anymore. I mean,
Oh, no. Oh, buddy.
You're going one big
Oh,
bam.
no. Okay. So here's what's gonna happen. I'm gonna push it.
Okay.
You're gonna have your hand out so that it hits the spring, compresses, and sends it back to you.
Oh.
That's what I'm saying. Big whammy. Big whammy here.
Yeah.
Okay, now, we need to talk a little bit about energy. There's 2 generic types of energy in the universe, potential and kinetic. Kinetic is the energy of motion. Potential is stored energy. So this is the spring. So Mother Nature and potential energy have never gotten along. I don't know if it was an Instagram, Facebook, 8th grade dance. I don't know what happened, okay? They don't like each other. So when this hits Drake's hand, that spring is going to get compressed. What type of energy do you think that's storing? Potential. Mother Nature goes, I don't like you. And then Mother Nature is going to take that potential energy and change it back into kinetic. Okay? All right. So, you ready?
Yes.
Okay.
Through the weed.
That's nice. That's nice.
Let's do it again.
Okay, you ready?
Yeah.
You go for 2 for 2?
Push it harder.
Ah.
Sorry.
Ram it.
No.
Break the finger.
That's good. We got a slow table
That's nice. Okay. Now, what's the only thing that's going to change on the position time graph?
The way it's going back.
Oh yeah.
Would you have the dramatic pause at the top? No.
Jared, what are you
So
doing to
this
this thing?
is just, so your position time graph is just gonna go, now, everybody cool if this is the beginning of it? Because it starts fast and it slows down. At this point, it's gonna hit Nick's hand, right? Very quickly, right? Boom. So then what's the curve gonna do on the way back? Something like this. Kind of looks like a Hershey's Kiss, which leans to one side. Okay? So you're slowing down, boom, kind of come back. Everybody cool with this? Starting fast, ending slow. Cool with this?
Yes.
Show a direction change.
Yes.
Because what 3 things do you have to do to change direction?
Slow down.
Because this is what's happening here.
Yes.
Yeah? Now, if you go up here at the top, you're going to draw a tangent line which has a slope of
0.
That's when you're going to stop to change direction, right? And then you're going to speed up, and you're going to change direction. So we've got all 3 things happening right here. So this is bam, okay? Happens very, very quickly. Now, how can you show that same thing on a velocity time graph? Where's it going to start? Do not start it at 0. Start up here, then what?
It's gonna start on
Rolling, rolling, rolling. Now, at this point, it hits Nick's hand. What's it going to do?
Big bam.
Big bam. Big bam is indicated by, right? So it's going to come down here. Then what's it going to do? Cross, because we change direction. So what's happening here? What's the spring doing? It's coiling up. You're storing potential energy. Now, what's happening to that potential energy here?
It's being released.
Changing back into
Kinetic.
kinetic energy. Then it's going to leave Nick's hand. Then what's this going to do? Go back up like this. Now, if we let it roll long enough, what's this line going to do?
Go back to 0.
Yeah, it's going to go back to 0. Now, if you were to find this area, what would that represent in terms of what we just did?
Displacement
Which would be what? From where to where?
from Berkhampton.
Yes, from where I let go of it until it hit Greg's hand. And then, now, if you were to find this area,
Nick's hand back to you.
Nick's hand's back to me. If I add these 2 areas together, what do you think I should get?
0.
Mary, why the international sign for 0?
Because one's negative and one's positive.
This is true. But why should they add up to equal to 0? Your answer is right. It's going to be 0.
Because it comes back to the point it started.
Beautiful. Okay. What's my overall displacement?
0.
0. So if this is like 1.5 meters, this should be negative 1.5. Because you end up back to that origin. Okay? Nice.
So adding the 2 is total displacement?
Yes. Yeah. Okay. Stop that. Let me hit out the lamp.
Hey,
So
come out
here's
there.
the setup. Here's the wall. You're going to measure back 1.5 meters and put down a piece of tape. You can measure back another 1.5 meters and put down a piece of tape. Now, some of my first block students who did not listen to instructions left their tape on the floor because I told them to pull it up, and they didn't. Okay? So they're going to get yelled at on Monday or Tuesday. So if you trust first block, who's half asleep, then you can go ahead and use their pieces of tape. If you don't, then you might want to remeasure. Now, this is going to take a minimum of 5 or 6 people per group. Okay? So, because you're going to have to time a whole bunch of stuff. So, you need somebody to push the cart. Okay? Now, this is not a NASCAR time trial. Okay? You not get bonus points for denting my wall.
Why not?
No. Okay? Good. So, ideally, you're going to push this thing fast enough so it hits here and then just barely makes it back across this point. Okay? The reason that you want to go slow is because you've got to time these events, and if it's going really fast, it's hard to get precise data. Okay? So, let's say McGriddle is doing the pushing. Okay? So he's going to give it a push. So,
You can do it later.
God forbid I get to teach.
Joel. Oh, Joel.
Shoes. Right up.
Dude, they let it.
Show him. Slap those slippies against each other.
Right up.
Bro game, I have some too.
Show the camera, Joel.
Show the
camera. Oh,
Them
baby.
boys light up. Pretty everything's gonna think we're so weird.
Really? Ooh, I tease you when I think that.
Thank
What does that mean about you?
Appreciate it.
I don't know.
Are we all creative influence?
You're the one who taught us to be this way.
And teachers are.
I learned it from you, Dad.
There could be worse influences, let's put it that way. Okay. All right, so McGriddle's gonna push it, right? Now, listen to me, listen to me, listen to me. Do you include the push?
No.
Okay? So this already needs to be moving when it crosses this point. Now, to make this simple, we're actually going to make this the reference point, and we're going to make the wall be 3 meters. So even though you're measuring backwards, we're going to start here. So this is 0, 1.5, 1.5 to 3, 3 to 1.5, 1.5 back to 0. So here's the deal. You need 4 people timing this. Okay? You need 4 people timing. So like grape might be timing from here till it crosses 1.5. But you have to make certain that you're judging this based upon the leading edge of the plunger. That's going to be that's what we're going to measure everything from. So grape is going to start it when the leading edge of that plunger crosses here, and then he's going to stop it when it crosses 1.5. Okay? Go with this.
Yeah.
Now, Nick 2, he's going to time from 1.5 to 3. So he is going to start his, ideally at the exact instant that grape shuts off his timer. So it's like a transition, passing off the torch. Now, here's what's going to be important. Listen to this. Nick 2 is going to stop his when this plunger is fully compressed and it's all potential energy. So when you stop yours, the plunger is like this and the cart has stopped. Okay? Go with this. Now, let's say that Shively is going to time from here back to 1.5. So ideally, as soon as, at the exact instant that you stop yours, Shively would start his because he's timing it on the return trip going back. But you have to be careful. You can't stop yours until that leading edge of that plunger has crossed that point. Otherwise, you're going to be off by the length of the cart. Then, Matt might be timing it from 1.5 all the way back to 0. Okay? So, you're going to have 4 distinct times. Now, you're going to have Bree timing the entire thing. So, she's going to time it from here all the way back to here. So, what should happen is that her time, when you add them all up, should be within 1/10 of a second of the sum of the individual times. So Bree's just doing this to make sure that that nobody really has a jacked up time in terms of when you add all this together. They don't have to be exact, but they should be pretty close. Okay? So your time here, time back, time back. Which time do you think should be the smallest value?
0 to 1.5.
Why?
Because it's when he's going the fastest.
Yeah, I mean, you haven't always started to slow down. You have the most kinetic energy, right? Which time do you think should be the longest?
1.5 to 0.
1.5 back to
0. Or the intent.
So, to calculate the velocity over this interval, what we're going to do is take advantage of the idea that velocity is displacement divided by time. Now, from the trip to Kansas City, when we did that analogy, how are you going to determine displacement?
P minus P naught.
What, somebody said it.
P minus P naught.
P minus P naught. On the way in, what's your initial position?
0.
What's your final position?
1.5.
1.5. Then you're going to go 1.5 to,
3.
then you go 3 back to,
1.5.
1.5 back to
0.
0. Okay? That's going to be your sequence. So on that column here, where you've got displacement, and in big bold letters I say be sure to show any calculation. So you have to calculate 2 things initially, displacement and velocity. So I want to see how you got the value of the displacement. I want to see how you got the value of the velocity. So, main thing you got to do today is get the times down. Then you're going to draw a position time graph and a velocity time graph. Now, on the velocity time graph, down below, I've got this deal to show you when you can determine the exact point when the plunger came in contact and when the plunger left. Typically, it takes about 0.2 of a second for that plunger to collapse, store energy, and then release it back. So, your position time graph is going to look just like we talked about. It's going to look something like this, right? Here's what's most vital, is that whatever point in time your position time graph has a tangent line of 0, what should be happening on your velocity time graph?
It should cross 0.
That's when it should cross the x-axis. So whatever point you have here, transpose this down to your velocity time graph. Because both graphs have to show the same thing at the same time. So if you want to determine the point in time when the plunger hits, let's say that this took like, let's say up to this point was like, I'm just going to make it simple. Let's say it's 2 seconds, whatever it is. That's when it came to a stop. So what that means is that if you subtract 1/10 of a second, at 1.9 seconds, that's when it hit to make it slow down. Then it took another 1/10 of a second to make it speed up, which would get you to 2.1. So that transition, when it's really steep, is going to take about 0.2 of a second. So use this elapsed time as your benchmark. Then you're going to scoosh it back a little bit, and then you're going to scoosh it forward a little bit, and then that's how you're going to draw your line. Now, here's what's going to frustrate you. You are more than likely to take my name in vain on this lab, because you're going to have to think. You cannot play connect the dots on the velocity time graph. You're going to have to think of what's happening. You're going to have velocities that are over intervals, not exact points in time. For 12 years on graphs, you've played connect the dots, and you all are phenomenal at playing connect the dots, okay? This one, you can't play connect the dots. But you can think it through and go, hey, when is this thing going fastest? Right, it hit the wall. Oh, slow down. Bam. How am I going to show bam on this graph? Okay? How am I going to show the bam that makes it speed back up? Okay? It's going to require some thinking. Now, before you all even start, you're only going to do this one per group. You're going to draw a position time graph and a velocity time graph for the cart rolling and stopping, and for the cart rolling and bouncing back. Okay? So have somebody get out a sheet of paper, one person, but make sure everybody understands this. And what I want on that velocity time graph, and only on the velocity time graphs, I want you to label when it's slowing down and when it's speeding up. So before you start going over, hey, viceroy of velocity, is this right? Once I sign off on it, then you can actually start to get the data. Okay? Are we cool? All right, go, lab 3. Now, if you want to use your phones as timers, use your phones, okay?